Welcome back to section 4 of chapter 4. This section's on modeling and optimization. So now optimization is just finding the maximums or minimums to make something the best. So a lot of this is going to be finding those extreme values. So that part isn't the difficult part. The difficult part is going to be the modeling, the setting up the equation to make it do what we need it to do. You've actually been doing some of this ever since at least Algebra 2, maybe Algebra 1, where you had to find the maximum value of a parabola. Now that we can use calculus, it actually becomes a little bit easier to do that. So our learning targets: answer optimization questions involving numbers and geometry, solve applications involving optimization of length, area, or volume, solve applications involving optimizations of quantities related to motion, solve applications involving optimization of quantities related to business or economics. And that one is the one that's a little bit different than the rest of them. The rest of them, the process is the same, it's just what is the topic. That's really the only difference. And then find parameters such that functions have given characteristics. So, first thing we want to see is some strategy. How can we go about doing this? And so these are just word problems. So we have some strategies. First, you need to understand the problem. What is it asking you to find? What information is it giving you? And then develop a mathematical model of the problem. Draw pictures. This right here is one of the biggest steps that people take who are successful. They draw a picture. And then label the parts that are important to the problem. Introduce a variable. We don't know something. What don't we know? Give it a name. And then use a variable, right? The function's extreme value gives the information sought. If we're trying to find the maximum volume, we should have an equation that says volume equals something. That should be the equation. So that's what we're looking for. Identify the critical points and endpoints. So where's the derivative 0 or fail to exist? And then the endpoints, that domain. Solve the mathematical model. And then interpret the solution. Make sure it makes sense, but give the answer back in whatever the problem's asking. The mathematical model is just a number. You need to change it back into an answer. So let's take a look at some of these. First example, find two numbers whose sum is 20 and whose product is as large as possible. So we have two numbers whose sum is 20, so we've done these problems before. X plus y equals 20, and whose product is as large as possible. So the product equals x times y. Well, that's a lot of variables. Well, here we can get y equals 20 minus x, and so we can substitute that in. So the product will be x times 20 minus x. We could multiply this out. 20x minus x squared. Now, if we were graphing this, that would just be a parabola. It's just going to be a parabola there. And it's actually not going to be a parabola there. It's going to be a parabola because when x equals 0, the product equals 0. So something like that. Now, why would it go back down? Well, because as x is getting bigger, 20 minus x is getting smaller. And so when x equals 20, y is going to equal 0. So this is going to be x equals 20, x equals 0. So our domain will be from 0 to 20. Now the product at those points is going to be 0. That will not be a maximum. That will be a minimum. So we want to figure out when is a product going to be a maximum. To do that, we want to find the derivative. Where is the derivative equal to 0? It's not going to fail to exist here. It's a quadratic. So we want p prime will be 20 minus 2x. Set that equal to 0. So we get 2x equals 20, x equals 10. So x equals 10 is not an answer. The question is find two numbers whose sum is 20 and whose product is as large as possible. Well, if x equals 10, then y equals 10. So our answer would be 10 and 10. Generally speaking, anytime we have a problem that's just like this, it will be a perfect square. So if we wanted 30, had the sum to be 30, it would be 15 and 15. That's just how that works. It can be changed if we add another piece into it, where like one of them is twice the other one or something like that. But our two numbers are 10 and 10. And notice in this case, it doesn't ask what the product is. It just says find the two numbers to make the product as large as possible. Another example. A rectangle is going to be inscribed under one arch of the sine curve. What is the largest area the rectangle can have, and what dimensions give that rectangle? A lot of times this is going to be inscribed under a circle, or it's inscribed under a parabola, or something like that. I chose to do the sine curve because I think this is actually a harder problem than some of those other ones. So what does it look like? It looks kind of like this. We have an arch of the sine curve, and so sine starts at 0 and goes to pi. We need some values. So this value could be x. If that value is x, that means that this value is going to be pi minus x, because the sine curve is going to be symmetric. If we go in a certain value from one side, we go in a certain value from the other side. Then the y value can be sine of x. And that's going to be the same for both of them because it's a rectangle. It's going to have that horizontal top. So we want a rectangle to be inscribed under one arch of the sine curve. What is the largest area of the rectangle can have? What are the dimensions? So the area of a rectangle is going to be the length times the height. So the length is going to be whatever the bigger one is minus the smaller one. So it'll be pi minus x, which is pi minus 2x. And the height is the y value, which is sine of x. So we want the area is going to be pi minus 2x times sine of x. And we want the maximum area here. So we need to find the derivative of this. The derivative of this is going to require product rule. We have u equals pi minus 2x, v equals sine x, du, pi is a constant, so that goes away. So minus 2x becomes minus 2. dv is cosine x. So now our derivative of our area is going to be negative 2 sine x plus pi minus 2x times cosine x. We want these to be, we want it to equal 0. Sine x plus pi minus 2x cosine x. And so, to find out where this equals 0, we could distribute the cosine, but is that going to do a lot of good? Maybe, maybe not. This one is one that it's going to be a tough one to try and manage by hand. So let's take another option here. Let's graph that and see where it might cross. And so when we graph it, and you would graph this using technology. When you graph it, you get something looks kind of like that. And then if we find that value, that intercept is 0, when you find this, we get that it's about 0.71046. So that would be the x value is 0.71046. The question was not asking what is x. The question is asking what is the largest area the rectangle can have and what dimensions give that rectangle. So for that largest area, we're going to plug that into the area equation. Area equals pi minus 2 times this 0.71046 times sine of 0.71046. And again, that you're not going to do that in your head. That you're going to use a calculator for that to get about 1.122 square units, because it doesn't actually give us a thing, so it's units. And then what dimensions give that rectangle? So the dimensions, it's not 0.71046, that's x, that's not the dimension. The dimensions, we're going to have pi minus 2x, and we're going to have sine of x. So pi minus 2 times that is going to be about 1.721. And sine of that's going to be about 0.652. So we have units long and units tall. So sometimes we'll get to things where you're just going to look at them and be like, geez, I don't even know how to even start setting that equal to 0. Graph it. You have tools. And then the answers are going to be possibly unpleasant. Another example, and this is a fairly typical type example. We've seen this a few different times, not this year, but we have seen it in the past. An open top box is to be made of cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. What does that mean? That means this. We have a 20 by 25 inch sheet of tin. We cut out x's and we bend up the sides. That makes the height of this x and the two side lengths 20 minus 2x and 25 minus 2x. So x is going to be limited, right? X has to be less than 10, otherwise 20 minus 2x is going to give us a negative number. And x has to be greater than 0 because, well, it's a positive value. But if it was 10, we'd just be cutting it in half right there, and that wouldn't do us any good. So, write the volume of the box as a function of x using appropriate units. What is the relevant domain? So, v of x is, well, we have our sides. We have x times 20 minus 2x times 25 minus 2x. That's v of x. We know the domain is going to be 0 has to be less than x, which has to be less than 10. So it has to be greater than 0, not less than or equal to, but it has to be greater than, because if we cut off 0, then we're not actually cutting off anything. And it has to be less than 10, because if it was 10, we would actually just cut the thing in half, and that wouldn't do us any good. And now we're going to have to find the derivative, dv over dx. looking at this, this is a triple product rule. I don't want to do a triple product rule. Let's multiply this out and then find the derivative. So v of x is x times 20 times 25 is 500. Then we have minus 40x minus 50x is minus 90x plus 4x squared. Distribute the x. 500x minus 90x squared plus 4x cubed. All right, now we can take the derivative. So dv over dx, I'm going to start with the 4x cubed, so we're going to reverse the order here. So that'll be 12x squared, and then minus 180x plus 500. So find the dv. Oh, and this would be inches, so the volume would be cubic inches. The dv over dx would be cubic inches per inch, which is kind of weird. It's cubic inches of volume per inch of x that we're taking off the side. Kind of almost want to make that square inches, but it doesn't work out that way. It's cubic inches per inch. Strange. So then using appropriate units, interpret the meaning of dv over dx in the context of the box. That would be the cubic inches that the volume is changing for every inch of x that we're taking out. Find the value of x that will maximize v of x and justify your answer. So we need to set this equal to 0. So I'm going to go up to the top. 0 equals. Let's factor something out of this, shall we? Let's factor out a 4. Everything here is divisible by 4. So we're going to have 4, and that's going to leave a 3x squared minus 45x plus 125. So let's see, 125 is 25 and 5 times 3. No. We have, let's see, 125 is a few other things, but that's not going to work out. But what we do have, however, is a quadratic. So we can use quadratic formula here. So we'll have x equals negative b, so that's 45, plus or minus the square root of b squared, 45 squared minus 4 times a times c, all over 2a, so 3 times 2 is 6. So doing a couple quick calculations here, 45 squared is 2025. 4 times 3 times 125 is 1500. 2025 minus 1500 is 525. So that gives us x equals 45 plus or minus the square root of 525 over 6. And the square root of 525 is 22.9-ish. So we're gonna have this rounded. Let's go 22.91. So x equals 45 plus or minus 22.91 over 6. So we have 45 plus 22.91 divided by 6 gives us 11.31, which is bad news because that's outside of the domain. And then we have 45 minus 22.91. What was that divided by 6 is 3.681. And that one's inside. So that has a possibility. And the endpoints could have a possibility. Now, if x equaled 0, the volume's going to be 0 because that's the height. If x equals 10, that side 20 minus 2x equals 0. So that gives us another volume of 0. So the endpoints give us a volume of 0. So this x equals 3.681 inches will give us the value of x that will maximize the volume. We could do a sign chart using v prime of x, or dv over dx, and we have that 3.6 something. When it's below that, the derivative, we can just plug in like 1 and find out that, oh hey, that's going to be a positive value. When it's above that, we could plug in 5 and say, hey, look, that's going to be a negative value. So that gives us a maximum. We could also justify it because it's going to be 0 and 0, and then plug this in, it'll be a positive value, and that means that it would have to be the maximum. Using appropriate units, interpret your answer in the context of the box. So when we take off the 3.681 inches from the square on each of the corners and fold the things up, that will give us the greatest volume of the box. Have we had to find the volume? Find the value of x that will maximize the volume. We have not actually had to find the actual volume. If we wanted to do that, we would just plug the 3.681 into the equation. I'd recommend really into that equation. I think that would be the easiest one to plug it into. But we could find the volume of the box as well. So some economics questions. Now, economics are kind of weird. Like, first of all, the maximum profit doesn't necessarily happen when a profit equation equals 0. Maybe it would, but we don't always use a profit. We usually use cost and revenue. But in addition to that, economics uses some different vocabulary to mean the exact same stuff. So, first of all, to maximize profit. Maximum profit occurs at the production level at which the marginal revenue equals the marginal cost. Remember, the marginal revenue is R prime, and the marginal cost is C prime. That just means the derivatives of those. So the maximum profit happens when the revenue and the cost have the same slope. The same thing with the maximum loss happens then. What does that mean? So if we have our marginal, or we have our revenue and cost functions, so when they are equal to each other, that's when you break even. The cost, what you bring in is equal to what you bring out. There is no profit. So the time when they are the most distant is when their derivatives are equal. That's when they're most distant. Then they start getting closer to each other. So like here, the revenue is still above the cost. We're still going to make money, but we're just not going to make as much money. Down here where the revenue is below the cost, we're actually losing money. We have to get to at least that point to start making money. And then if we sell too much, we start losing money again, which seems kind of strange. You wouldn't think that would happen, and it probably doesn't happen all the time, but in this graph it does. So how can we do this? Well, suppose R of x, the revenue, equals 9x, and the cost, C of x, equals x cubed minus 6x squared plus 15x, where x represents thousands of units. Is there a production level that maximizes profit? And if so, what is it? We need to find the derivatives of both and then set them equal to each other. R prime of x equals 9. So notice that's not the graph we're looking at, by the way. C prime of x equals 3x squared minus 12x plus 15. So we just need 9 to equal 3x squared minus 12x plus 15. Subtract 9 over to set it equal to 0. I almost wrote plus 15. 15 minus 9 is plus 6. We can factor out a 3. X squared minus 4x plus 2. And then we're not going to be able to factor that, but we could throw it into a quadratic formula to get negative b is 4 plus or minus the square root of 4 squared, 16 minus 4 times 1 times 2 is minus 8 over 2. So x equals 4 plus or minus the square root of 8 over 2. So square root of 8 is 2 root 2. We divide everything by 2, so that's 2 plus or minus root 2. So we can make a sign chart. We'll have 2 minus root 2 and 2 plus root 2. Now, if one of these went negative, that would be problematic. We wouldn't want to use that because it would the x is the number of things we made, so we can't make negative things. So we do want to keep x positive here. And so we could do these, we could graph these as well. Oh, so it's going to happen at, there we go, we don't even need to make a sign chart. It's going to happen at one of those. We need to plug those into the original functions to see which one's bigger. So if we plug in this first one, 2 minus root 2, we get that the revenue at 2 minus root 2 is less than the cost at 2 minus root 2. And so that's going to give us the most loss that we get. If at 2 plus root 2, we get that the revenue is greater than the cost. 2 plus root 2. And so 2 plus root 2 will give us that maximum profit. And you can see that by graphing it as well. You can see which one's bigger than the other. And the last one, the minimizing the average cost. So the average cost, it says the production level, if any, at which the average cost is smallest is a level at which the average cost equals the marginal cost. The average cost, C of x divided by x. We need that to equal C prime of x. That's the marginal cost. So if we have, suppose C of x equals x cubed minus 6x squared plus 15x, where x represents thousands of units, is there a production level that minimizes the average cost? If so, what is it? So we have C of x over x. Well, they all have an x in it, so that's just x squared minus 6x plus 15. And then C prime of x is going to be 3x squared minus 12x plus 15. We want to set these equal to each other. So x squared minus 6x plus 15 equals 3x squared minus 12x plus 15. We can subtract everything over this way to get 0 equals 3x squared minus x squared is 2x squared. Add the 6x, so negative 12x plus 6x is negative 6x. Subtract the 15, well, that goes away. So we get 0 equals, we can factor out a 2x, have x minus 3. So here x equals 0 or 3. And so if we look at plug them in, this is where the average cost is the smallest. So if we make nothing, the average cost is the smallest. I mean, that makes sense. I made no paella today. It cost me nothing. There we go. And then if we made 3,000 units, so when x equals 3, that will give us the average cost, or the minimum average cost for actually making something. So 3,000 units is what's going to give us that cost. So again, the economic stuff, we're doing the same stuff. We're finding derivatives. We're not setting it equal to 0 necessarily, which is kind of weird. But we are just finding derivatives, and then we're finding where stuff does equal 0. We just may have to add or subtract stuff. And then, yeah, it's the same stuff that we've been doing for a while. So, with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.